Hello, and welcome to this Smiths Interconnect webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenters. With us today, we have Harold Akins. Harold is a Global Product Line Director of RF at Smiths Interconnect. Also here today is Alan McNeil. Alan is a Product Line Manager of Ferrite and Waveguides at Smiths Interconnect. To read more about our presenters today, please look at the speaker bio window right next to the main presentation window. So gentlemen, with that, I'd like to pass things along to you to get this webinar started. So go right ahead.
Good morning all and welcome. Like Katie said, I'm Harold Akins. Glad that you join us. For today's agenda, we'll discuss SSPA technology, including exploring the capabilities, benefits, and added value when using an isolator on the output of a solid-state power amplifier. We'll learn the technical challenges that you might face as isolator designers to ensure the product's success. And finally, we'll understand the future of the SSPA isolator market. Without further ado, I introduce you to my product line manager for ferrites and waveguides, Alan McNeil.
Hi there, everyone. Thanks for attending today's event. My role as product line manager, as Harold says, is for ferrites, which includes isolators for SSPAs. I'm based in Dundee in Scotland, to the north of the UK. And I'm going to kick off things by asking you a question. So, Katie, do you want to go through the questions?
Yes, thank you so much, Alan. So everyone, this is our polling question. So I'll ask you the question, and then please choose an answer that best describes how you feel with this. In our experience, what kind of issues have you experienced with isolators used on the output of an SSPA? So our first choice is they can't handle the reverse power the way I expected. The next one is the electrical performance was not as I specified. Next option is there are some reliability issues. Next one here is mechanically they are challenging to integrate. We do have the option of choosing all of the above. And then below that, if you've never experienced an issue with high power isolators, our supplier provides flawless products. So I'm going to give you a few seconds to answer that question. So everybody choose your answer. All right, everybody, I'll give you a few more seconds to submit your answers. Your feedback is important to us. All right, everybody, thank you so much for taking a second to give us your responses. I'm going to push us out to our results. And Alan, if you'd like to chat about these results, feel free. So everyone, here's the results that we have so far.
Thanks, Katie. Well, clearly 18% are all our customers. Thanks for that vote of approval. Yeah, it's a fair number of broad-based issues. I'm encouraged that there was no reliability issues, but I'm not surprised that a quarter of you said they had something that was wrong with them. So I think we're going to address all of these points, or all of these answers, as we go through our presentation. So I'm just going to advance it to the first slide, and over to you, Harold.
So, Alan, when we speak of a ferrite isolator for a solid-state power amplifier, what exactly do you mean?
Well, Harold, the solid-state power amplifier needs no introduction. The companies producing them are our customers. We supply them high-power ferrite isolators, which are specifically designed to operate in assigned bands somewhere in the range of about 250 to about 20 gigs. These SSPAs are used in a variety of applications, including communications and radar systems, and they're used in space, commercial, and defense environments. Now, most of the products we supply are isolators, but in some cases we also supply circulators, and sometimes occasionally with remote package loads. Now, as you can see on the screen here, we've got an image of an SSPA. This is a public domain image of an SSPA in L-band that was developed by the European Space Agency. And as you can see, or if you can identify, there are actually two isolators. There's the one with a little black dot in the middle, and that's an interstage isolator. Then there's the chunkier fellow on the output, which is a high power isolator, and that actually includes the interface, the TNC connector interface to the SSPA. So if I
So why use an isolator on the output of an SSPA?
As far as we're concerned, Harold, there's two fundamental reasons. The first one would be impedance buffering. SSPA gain stages tend to have relatively poor return loss, and 2 to 5 dBs is not uncommon. And these gain stages operate best when they're driving into a defined impedance, and that's where the isolator comes in. So by employing an isolator, the designer can match the gain stage into a stable impedance, and by doing so, achieve a more stable performance, no matter what is happening downstream after the isolator. So, for example, if you put a 20 dB isolator with a 20 dB match after the final gain stage, as you can see in this schematic here, that will result in a return loss looking into the output of the SSPA of approximately 18 dBs. Now, the actual answer you get would depend on the output stage of the gain stage and the return loss, but basically that's an impedance buffer. I guess the second reason is the fault condition. Now, under normal operating modes, the power is going into the isolator and out of the SSPA, but the fault mode refers to a scenario where the output power is directed into the SSPA. Now, this may be due to a fault in the system. It could be an open or short circuit due to a faulty component, or it may be due to some operating mode, or it could even be due to a jamming signal. But in any case, the isolator is expected to observe this power under any circumstances and for an indefinite period of time, and by doing so, protecting the SSPA. Now, of course, employing an isolator in this way doesn't come for free. There's obviously the cost of the device itself. It has a mass and volume penalty, and as you can see from this image, the large output isolator isn't exactly miniature. There are bandwidth limitations because an isolator is, when it's optimized, tends to be relatively narrow band and certainly narrower band than the chipsets that would be used. And there's an insertion loss penalty. Now, the insertion loss is always a topic of conversation. Our customers, our designers that we deal with are always trying to minimize insertion loss, and we understand this. It's not uncommon for us to argue over a few tenths of a dB or a few hundredths of a dB. Now, we all know that the SSPA will then be connected into more or less indeterminate length of cable, but we do appreciate that insertion loss is important.
So all SSPAs use isolators?
I wish that was the case, Harold, but it's not. Due to the practical limitations of broadband isolators, they struggle to handle high RF power levels. The corollary being that high power isolators tend not to operate over wide bands. So a typical high power coaxial strip-line ferrite device will operate over a 5 to 10% bandwidth, and you'll get a very good performance over that. You can get wider band performance from a microstrip type, say up to 20%, but these are generally the limitations of high performance. So if you're designing a broadband system such as an 8 to 18 gigahertz jammer, you'll struggle to identify an isolator able to operate over this band, let alone be able to handle the high power. So fortunately for us, there are many classes of applications where the ferrite isolator is an ideal technical solution, offering a good balance between performance, cost, and reliability. One of my jobs is to ensure our customers' needs are understood so that we can support them to identify practical and affordable technical solutions and what trade-offs, if any, we need to make. Or, in the case where it's not possible, it's impractical to do this, to ensure the customer understands why.
So what makes our SSPA isolator special?
Well, I'd like to think they incorporate features which makes them special, Harold, but all SSPA isolators are deemed critical because of single-point failures. Put another way, the reliability of the SSPA depends on the isolator doing its job under any circumstances. So here we have an image of an L-band isolator. Now this particular device is very new, and it's designed to be attached to the SSPA but mounted on the output of the SSPA, external to the box, and the interface, the input to the isolator actually passes through the bulkhead. Now in this case we would consider this device to be relatively straightforward, but our customer requirements were particularly challenging. First of all, we had to meet an extraordinarily tight mass budget and comply with what we would consider to be non-optimal mechanical mounting requirements. Now, this particular device had to operate over an unusually broad frequency range. Now, it's 1.14 to 1.31 gigahertz, and while some people might not consider that to be high power, or broadband rather, it is actually for a high power device, particularly broadband. And it had to have minimal loss. Obviously, everyone wants minimal loss, and combined with what I would class as exceptional isolation and return loss in excess of 23 dBs in this case. The device itself has an input which is a custom input. It's actually a TNC socket, so you can see to the bottom left hand of the device there's a socket interface, and you can probably discern that there's a flange which actually bolts onto the customer's SSPA bulkhead. And there's the gold-plated finish, which is obviously gold-plated, which we don't use for low loss. We actually use that to maximize the multi-paction margin under a vacuum. But then we start to look at some of the constraints that this device had, and it had to handle the reverse power when mounted on a heatsink at plus 90 degrees centigrade. Now, our customer couldn't make this any colder, which means this base plate had to operate at plus 90 degrees C, and that's before the power is applied. Now, the heatsink, the 90 degree heatsink, had a very limited thermal capacity. So in point of fact, it couldn't handle 150 watts over a small surface area, and we had to increase the size of the isolator so that we didn't overload the heatsink. And the last thing is the device had to have a multi-paction margin of 12 dBs. And what that means is this 150 watt device had to be tested in a vacuum to 1.2 kilowatts, which is about 8 times the power. And that's under circumstances where we were bombarding it with radioactive particles. So to meet these challenges, we had to employ most of the tools in our chest, and I want to spend a few minutes discussing these and explaining why they're important. So I guess the first thing to try and understand is if you see the diameter of this junction, that's about 1.5 inches. So that's about 40 millimeters. So you can begin to see it's quite a large device. And the housing is made from a special grade of stainless steel. Now, this stainless steel is used primarily for its magnetic properties to constrain the magnetic field that biases the ferrite within the junction. But the other reason we use this particular grade is it's a particularly poor conductor of heat. Now, for a high power isolator, you might wonder why that is important, and I'll come to that in a second. We have a high conductivity oxygen-free copper base plate and load, and that's used because this grade of copper has an extraordinarily good thermal transfer properties, and we need that so that the heat can get transferred down into the heatsink. Now, the connector is, as you can see, the TNC connector. That's the output of the SSPA. It's compatible with TNC connectors, but it's one of our own design. And in fact, the internal structure is specifically designed to handle high power. And this TNC connector is actually machined to be integral with the stainless steel housing. So it's a single piece of metal connector and isolator body. And this means we get extraordinarily good EMC properties. And the last thing I want to focus on is the load. As I said earlier, we're trying to transfer 150 watts in the fault condition into the heatsink. And because of the heatsink limitations, we had to extend the load around the back of the isolator. And I apologize that it's not immediately obvious, but there is an image later on showing this. And that load is comprised from board-level components that we buy from a sister company, Smiths Interconnect USA. Now, we couldn't just use a chip termination. We had to use a series of attenuators and chip attenuators and terminations, and that's purely just to make sure that the heat doesn't overload the heatsink. Now, internally, it's not obvious because this is an external shot. We've used various materials and processes to maximize the electrical and thermal performance, and to optimize the peak power handling, we used a combination of circuit design, vacuum brace, thermal paths, and a recently qualified multi-fraction suppression process. Now, it all looks rather complicated, but I can assure the listeners that none of these features or materials would have been used unless they contributed to the reliability and electrical thermal performance of this isolator. So it's a custom isolator solution that we're offering, and you can see here that they come in all different shapes and sizes. In fact, a bewildering range of shapes and sizes. Depends on the interface. In this case, we've the top left indicates a TNC output and a TNC male input. We've got some microstrip devices here, and this particular device each device is about 7 millimeters by 7 millimeters. And it doesn't work in an SSPA, it works in a TR module. So there's a power amplifier feeding one port, there's a receiver on the other port, and the third port's attached to the antenna. Now this device was qualified in a vacuum to 50 watts CW, and it operates over a 20% fractional bandwidth. Now that's not bad when you consider that this device only weighs a quarter of a gram. Here we've got an example in the middle of a device which has a strip line interface, and as you can see they come in a variety of shapes and sizes, from about UHF to K-band, and a variety of applications as well. The products here are for defense and space applications. And on this slide we've got an example of a few commercial parts. This device here is actually used on air traffic control radar, and it's got to handle 5 kilowatts peak into a short circuit. So in point of fact, under the fault condition, this device is seeing 20 kilowatts of peak power. So I guess this sorry, let me just take that back a slide. If I was to look at all the devices that we've supplied for SSPA and TR module applications, the count would be roughly 830,000. The majority of these, about 700,000, have been used in TRM applications, primarily in C and X band. It's about 160,000 have been used in terrestrial radar applications, mainly defense, ranging up to about 4 gigahertz. And there are about 70,000 of parts in space-based applications, currently in orbit or in a deep space mission.
Alan, you mentioned earlier in the presentation that our isolators are a single point of failure. What are the technical challenges that we face as isolator designers to ensure that our products do not fail? And Alan, when you answer, there's a slight reverberation, so you may want to back up off your microphone a little bit.
Okay, thanks, Harold. Is that any better?
I think so, yep.
Okay. Well, what do we do to ensure our isolators do not fail? There are many things that we do, and there's many things that we have to consider, and it really depends who you're speaking to. There are hard failures and there are soft failures. In other words, failure to meet your customer's stated needs, and the soft failures are failure to meet your customer's unstated expectations. So in the slide that everyone can see here, I'm going to use our real-world example. It happened around 15 years ago. We had a customer who had an application where they wanted a low-loss SMA isolator. They'd seen what they wanted on a catalog. This is before the internet, and this device had a mass of 50 grams. But it had an insertion loss of 0.3 of a dB, and he needed something much, much lower. His target was 0.12 of a dB, and he needed to use this product aboard a spacecraft, where power handling was the absolute critical parameter. So very early on in the process, we identified that the SMA connector would not handle the forward power, not reliably at least, and that we had no choice but to use TNC connectors. So that made the device immediately larger. And to achieve the 0.1 dB loss, the device had to be made even larger still, and of course heavier. And to handle the potential reflected power, which in this case, 100 watts forward into a short circuit would be essentially 400 watts peak in the reverse direction, we had to include features in that device that made it even larger. So with all these constraints, the device was no longer 50 grams, and rather than 0.3 of a dB, we managed to get a 125 gram device rather, with an insertion loss of 0.12 dBs. And to be honest, we were very lucky because the customer we were dealing with understood these issues and had been willing to compromise. Now, had they not been willing to compromise, unfortunately, we would have had to decline to support this customer because we would never knowingly have offered an unreliable solution. So we took this solution to the mechanical engineer, so our customer's colleague, and then we realized that we had another problem because the heatsink that they were going to dump this power into wasn't man enough for the job. So in point of fact, the 125-gram device became even larger still. Now that was a real issue because of the vibration requirements and because of the various other mechanical constraints. So we had to do a ton of weight relief to get the device down to the size that it was. Now in the end of the day, we actually supplied to the customer something they wanted, something that they needed. But did we fail? Well, we failed to meet their expectations in some ways, but we succeeded to explain to them why we had to make the trade-offs we did. So they did get the product that they needed, and they did actually avoid the very real risks posed by the operating conditions. And we managed to do that using our experience through technical analysis and actually be able to demonstrate this through test.
So you talked a lot about space. Are the challenges the same for space and terrestrial applications?
Well, they're basically the same, and the process of arriving at the end solution is similar. I guess the big difference is the relative importance in how we address some of the critical requirements. So, for example, space brings with it the increasing complexity in terms of the unusual effects that can be experienced when one applies RF power in a vacuum. And of course, there's no chance to fix something in space once it's been launched. So with these things in mind, cost is usually the first casualty when designing a product for space. On the other hand, terrestrial applications tend to be technically easier, less challenging, but commercially more difficult. As in the limit, you can always repair or replace a faulty component. So fundamentally, it's about trying to meet a spec in a defined volume, in a defined operating environment, and doing this reliably and repeatably and affordably. But fundamentally, the process is the same.
You know, power amplifiers have been around for a long time. Are the challenges still with us?
Well, in fact, Harold, I think the pace of advance, or the challenges are actually increasing because the pace of advance of new chipsets is proceeding at a phenomenal rate. The chipsets are increasingly efficient, they're increasingly affordable, which means more and more people can use them. They operate over ever-increasing broadbands, and so the number of applications that require them is extraordinary. And I guess the other very obvious challenge is that the operating frequencies are increasing dramatically. So as the operating frequencies increase in size, the SSPA isolators decrease in size, which makes the thermal challenges much more difficult than they would be at low frequency. So when I think back about 20 years ago, L-band SSPA isolators for space were new. And today we're seeing space-qualified SSPAs at frequencies of 10 gigs beginning to be quite commonplace. And I don't think it's going to be that long before we go beyond that into the realms of 20 gigs and higher. I think that the challenges are really, for us, thermal management, breakdown under a vacuum, electrical performance, device size and mass, and each one of these is driven by the increasing RF powers, increasing bandwidths, increasing baseplate temperatures, and tighter packing densities. And we're not going to touch on EMC today, but as you get these devices working closer and closer together, and we have a magnetic and EMC environment that we have to attend to. And of course, if you take all these things and you apply the fault condition for an indefinite period of time, then everything's impacted. So I think we have a question here. Katie, do you want to ask this question?
Yes, thank you so much, Alan. So for our audience, we are going to ask for your participation again. We have our next polling question. The question today is, in your experience, how easy is it to get the support you need from your RF component suppliers? And we have a couple options here for you to choose. First one is, it's very easy and we work well together. The second is it's challenging, but we get there. The third is it's hard and getting worse. And the fourth is I avoid dealing with suppliers at all costs. So if you guys can participate and give us the best answer that fits what you've experienced here, I'll give you a few minutes to answer that question. All right, guys, thank you. We appreciate your participation. I'll give you a couple more seconds for a few more people to get their answers in. All right, thank you all who participated in our polling question. I'm going to push out our answers now and see what our percentages were for responses. Alan, back to you.
Yeah, thanks, Katie. I'm actually not surprised at these answers. I'm glad that no one's chosen the last one, but it is actually challenging, and that challenge actually usually results in an extended period of time during development. So that doesn't actually surprise me at all. So thanks for that, everyone.
Well, you know, actually that polling question was pretty significant and telling at the 69%. So Alan, why don't you give us a sense of the typical product development time for the isolators? Yeah,
well, it usually goes one of two ways, Harold. It can start, and it normally starts with a discussion and a basic list of customer needs. And obviously the first port of call is to identify whether we have something in our portfolio that offers, perhaps with some adaptation, a suitable solution. And if we have a really good starting point, it can be as little as 14 to 16 weeks to complete the development. Of course, that depends on if we're doing any special testing. But if we're pushing the boundaries, it can be typically 6 months. However, these estimates don't include the time that we spend going back and forth with our customers trying to understand what they need and for them to kind of understand what we can offer. I guess the other way it starts is as an internal development. At Smith Interconnect, we have a constant stream of activity happening in the background as we develop and test new ideas and processes. And some of these are relatively simple. There was one recently that we asked the question, what happens to the performance if we remove the gold plating? Now, within a couple of weeks, we knew exactly what had happened. At the other extreme, we posed a question to ourselves some time ago, what do we have to do to increase the power handling by a factor of 2? And, you know, so it can take an indeterminate period of time.
And why do we do qualification testing?
Well, we do qualification testing. It's about understanding and hopefully retiring risk. You know, I said before that the SSPA isolator is a single point of failure, and we need to know that the part won't fail. So it's about risk mitigation. And we do that through qualification, and we can establish whether our design is robust, it's going to operate as expected, under the worst combination of operating conditions specified. We also use qualification to push the envelope of our understanding. So if we are qualifying for something for a customer, we will take it to the limit of the customer specification because that's the correct thing to do. But if we're doing it for ourselves, we'll often push a device to its absolute limits and sometimes beyond. But we don't tend to do that as part of a customer development. And we do that because we're very fortunate in having a comprehensive in-house manufacturing and qualification capability. And Smith has been very good to us in investing on site in RF power testing, both peak and average power, vacuum testing, radioactive seeded multipaction, critical power. I mean, we can do the whole gamut of high power, plus we can do the environmental stress screening tests for mechanical shock, vibration, thermal shock, even humidity, and of course EMC under reverberation chamber conditions. And of course, there's no point in having that qualification capability if you don't have the ability and tools to analyze the effects of such testing. So we have dynamic X-ray here, we have the high magnification optical, and we have device sectioning. So when you've got this capability, you're able to retire these risks, and that's what qualification is ultimately about. And we can also use the same kit as a development tool, because absent the ability to actually develop and improve your processes, it's very difficult to explain to your customers what kind of risk they're taking. So not all our competitors are able to make this boast, and they don't all have the capabilities we are fortunate enough to have and the investment it represents. But I guess that investment underscores our commitment to the technology and of our understanding of the importance of getting it right. So getting it right is usually very reassuring to our users or our customers, because like us, they actually like to enjoy a good night's sleep, knowing that their solution is in good hands.
Can you provide an example?
I can. On the screen here is an image of a TNC circulator. Now, the reason we use a TNC circulator rather than an isolator is it's actually easier to do the development on a circulator, understand what's going on, and then eventually convert that to an isolator. So we had an idea, it was about 5 years ago, and we posed the question to ourselves, how do we double the power handling of our isolators under vacuum conditions? Now at that time RF powers were trending upwards, and although we had a really good idea how to meet this challenge, we actually had no way to prove it. And our belief was then, as it is today, that if we can't demonstrate it to our own satisfaction, then we shouldn't even try to attempt to do that to our customers. But we were lucky, and as I've said earlier on, Smiths invested a huge amount of money to involve a qualification lab here in Dundee, and that included high power test and multi-paction facilities. So having been sitting on this idea for 3 years, we made testing this idea a very high priority. And believe it or not, within 6 months we'd managed to develop the concept, perfect the design, and qualify the working unit. So this is the working unit here. There's 1500 watts. We tested at 1500 watts peak going in, 235 watts of average power. And we put that into a short circuit any phase, and that meant we would be able to induce somewhere in the isolator, it's always difficult to tell, somewhere in the circulator, it's always difficult to tell, there was up to 6 kilowatts, and that 6 kilowatts comes from the 1500 watt wave going forward, superimposing on the reverse power. So that was 6 kilowatts, and to give you some idea of how much of an improvement that was, we were aiming for a ×2 improvement, and we got about a ×10 improvement. So we were pretty pleased with that. Now, I guess the only problem is that we actually don't know the limitation of this process. So we know it's good at 1500 watts, but we ran out of power. And because the qualification was successful, it didn't break down, it didn't fail. We actually don't know what this device would actually do. What we do know is that at 235 watts, the TNC cables that we were using inside the vacuum started to melt. So we understand that this device is more or less state-of-the-art, but it's background work. So if we want to take this device and convert this into a customer product, then we really have to understand the complexity of the SSPA environment in which it will be fitted, because the development can't really start until we sit down with the customer and start the process of understanding what it is precisely that they want.
So if you were to consider the future, what direction is the market likely to take?
I guess there's two themes, Harold. In terms of design, then we can use the past as a predictor to the future, and it's clear to probably everyone listening here, and come as no surprise that it's going to be more power, more higher RF power, packed into a smaller volume, operating at higher temperatures, and complicated by a general increase in operating bandwidth. I mean, today we're already shipping circulators, isolators, and dual junction isocirculators in assigned bands ranging from L to X, and we're working on the same KUK and SMT realizations. But in the coaxial strip line and microstrip domain, we're seeing a huge amount of effort in K and Ka band, and I don't think it'll be too many years before we see the powers going upwards of 100 watts, certainly at K band, in a coaxial form. So if the users have any unmet needs, or they want to understand in greater detail what we've done and what direction we're going, then we can point them to various resources on our web, or where we don't have it on the web, we can supply them hard copies. I mean, it's very important that we actually understand what our customers' roadmaps are. I mean, at the moment we're developing isolators all over the place. In fact, our most recent development is a high-power E-band device working in WR12, and that's a huge step forward for us and a huge investment. But we really have to understand our customers' roadmaps. Now, the other side of this, aside for the technical side, I mentioned earlier that the quantities of products that we're producing are actually increasing. They're becoming cheaper, they're becoming more affordable, and we have to find ways of making these in higher quantity. So at the moment, we are looking at our operational side, and we're already using automation to assemble simpler devices, and we see ourselves starting to design the products with automation in mind, as opposed to trying making the automation fit the product. So that's another way that we're looking at it. And the other operational and design aspect is that we're looking at a localization strategy. You know, at the moment we're talking about products that are designed and made in Dundee, but we're planning to establish a ferrite isolator and circulator design and manufacturing capability in the USA. And that's primarily to support demands from customers who are simply not able to deal with a UK design and manufacturing facility. So this is in the early stages, but the decision's been taken, and we in Dundee are going to be there helping our US cousins in supporting this new initiative.
Okay, thanks. Hey, I do want to remind the audience that if you do have questions, please search, use the blue blocks and answer any questions that you may have that we can go ahead and answer them for you. Alan, I got a loaded question for you, though, too. So, do we always get it right?
Tough question. Well, Harold, from the site, we release about 100 new products per year. And I would guess about 50 of these, about half, are very new. And around about 20% or 10 products I would class as new high-powered devices. And I think we get it right eventually, as the poll would suggest, that that's more or less what people expect. And I can't recall the last time we actually, what I might describe as a design catastrophe or a major schedule impact. But where we do get it wrong, it's usually because we've pushed the boundaries and underestimated the time that we need to get it right. So I would concur with the experience of our listeners and say that our biggest issue is probably underestimating the schedules. But, getting it right is always a question of how long it takes to get right. And when you've got the capability that we've got in-house, it does actually help contract these schedules. And of course, I can't overemphasize how important communication is both ways, letting your customer know what's happening. And of course, if the customer's requirements change, then obviously two-way communication helps in that street. So we're very fortunate here in Dundee to have an in-house experienced design team, manufacturing, engineering, and very fortunate, I'd say, to also have very understanding customers. I mean, these customers are contracting and trusting us to do a good job, and we do this based on the information we're provided. So I would say, do we always get it right? Yeah, eventually.
And how do we benchmark ourselves against our competition?
Well, it depends what kind of target market and product you're talking about, Harold. The number and strength of our competitors kind of depends on this. Certainly, it should be no surprise that the simpler the product required, the more competition there is. But I would say at the area that we play in, which is at the top tier, we have a few really good competitors. They're very competent. We know who they are. We respect and take them very seriously. And of course, we never underestimate them. In fact, we use the threat that they pose to drive our own efforts, as I'm sure they use our efforts to drive theirs. I guess the competition I struggle with are those that don't quite know what they're talking about. But boy, they tend to offer very low-cost products. And I guess the way we deal with this is to focus on supporting customers who understand what it is they need, they understand what we're offering, and you understand the value of what we're offering. I mean, as a supplier, Smiths Interconnect is technically extraordinarily competent, well-equipped, and able to scale to meet our customers' needs. I think we're amongst the safest pair of hands in the business, We've got excellent quality control. We've got excellent supply metrics. And when we commit to supporting someone, we do that unconditionally. So, yeah, we've got competition. Are we the lowest cost supplier? Absolutely not. I think if purchase price is at the top of a buyer's list of deliverables, then a few minutes on the internet will deliver a dozen so potential cheaper alternatives. But, you know, as I say, our customers are the ones who value what we do for them. They value our transparency, the support we supply, and above all, the reliability of the end product. You've got to remember that the systems that we provide our products for are expected to last 20 years in service. And the products that we deliver and provide to our customer have to hit their floor, production floor, and not causing them any additional problems.
So what message would you pass to prospective users?
Well, whoever your preferred supplier is, hopefully it's us, seek earlier involvement. You can't start that dialogue early enough. The worst thing that can happen is you've completed your SSPA, decide you want an isolator, and discover that there's no space to put it in. I think the other message I would say is involve all your internal stakeholders. And by stakeholders, I mean it's not only a microwave problem, it's also a mechanical problem, and it's also a schedule issue. So get all your colleagues together, decide what it is you need, work out what your own trade-offs are, and then get your supplier involved ASAP. I think the other thing I would say is to design a good, reliable product, you need some basics. You need to know where the SSPA operates. Is it in a vacuum? Is it on the ground? You need to know the operating frequency band. You need to know the incident power and preferred interfaces. So I would encourage transparency in sharing this information so that your supplier can come up with an optimal solution, and if needs be, to identify a trade-off. And I guess the last thing I would say is actually press your supplier on what risks they are taking with their design and what are their plans for mitigating their design through analysis and test. So that's what I would say. So I guess I've talked about what we've done for SSPAs, and I've mentioned that we're based in Dundee, Scotland. That's where the little green dot is, and that's a picture of our factory. Our product platform is based on ferrite isolators primarily, and circulators, but we also do transitions, loads, terminations, couplers, and hybrids. And we do these as low and high power components. We realize them in coax, microstrip, strip line, and waveguide. And we tend to focus on supporting the high rail markets, which are primarily radar and communication. And these products are designed and qualified in-house, and they range from UHF to E-band. And we make them in, let me just advance this slide. We make them in coax. It's a wide range of isolators, etc. And they start about UHF and they go up to about 30 gigahertz. Most of them employ our unique solid connectors. That's where the connector is actually machined onto the housing, and our patented internal structures. And they tend to be available in SMA and TNC. And all these products are optimized, even the low power devices, believe it or not, are optimized for dynamic environmental conditions, and obviously the higher power devices for thermal conditions. So we also do microstrip devices, as you've seen earlier. They tend to start at about 1200 megs and go up to about 33 gigs. I think the sweet spot for this technology starts around 5 gigahertz up to about 33 gigs. And they tend to be very broadband structured. They're tuneless. They can be designed to handle quite significant amounts of power, and they're very low mass. And we're currently working on surface mount and strip lines suitable for pick and place and reflow soldering. We also do waveguide, and that kind of ranges from passive sub-assemblies. You can see a sub-assembly there. We also do coax multifunction assemblies. They tend to combine a number of our in-house products, isolators, hybrids, couplers, what have you. And they tend to be designed for very specific applications and tend to be limited to space and defense markets. And then we've got the waveguide components themselves. They tend to be band limited. They can be broadband, but they tend to be band assigned. And we start about 1.2 gigs and we go up to about 52 gigahertz. And again, they're optimized. The other thing these components share in common is that for the most part they're tuneless, and we can qualify them in-house for quite extraordinary levels of dynamic shock, vibration, temperature. And as I mentioned earlier, we're pushing the boundaries. We're moving our design and development activities up to 96 gigahertz. So thank you very much for listening. We're going to have a Q&A session now, but I do want to thank you for the time you spent thus far. So Katie, are there any questions?
Sure, Alan and Harold. Thank you both so much for a great presentation. As you mentioned, we are going to move into asking some of the attendees questions right now. All right, guys, so our first question today, have you ever had one of your isolators fail?
I can say hand on heart that we've never had a field failure. And we've never had a failure in qualification or LAT. But that's because we spend a huge amount of time qualifying them. What I can say is we routinely get failures during the development process. But if you're not pushing the boundaries, then you're not doing enough. And I would say that's where we learn what we're doing wrong and how to get it right. So I don't class development as a failure, but it does happen, and very often this can result in extended development lead times. So in the field, no. In the development lab, yes.
Okay, Alan, thank you so much for that answer. For all of our attendees, I do want to point out that we have some great items in our resource widget today. Those are listed right below the Q&A window. So if you want to take those items with you before you leave today, now would be the time to start grabbing those. All right, guys, back to our questions. Another attendee is asking, what should we do to make defining and using such an isolator easier and less costly?
Wow. Okay, so I would say get your vendors in as early as possible, because the cost is not just the cost of the isolators, but it could be the cost to development of the SSPA. So early involvement, absolutely. And the most professional suppliers that you speak to will guide you in the pitfalls, and that will certainly make it easier. I think set reasonable expectations and don't over specify the part. What a lot of designers who design SSPAs don't realize is they can quite easily get, for example, a 1 to 2 gigahertz out of a chipset. But if you define a 1 to 2 gigahertz isolator, you're asking for trouble. You're going to end up with something that's far larger than it ought to be, far more expensive than it ought to be, and be performance compromised. So I would say set your expectations to be reasonable. And don't design any bells and whistles. When it comes to testing, if you need 100% test, then specify 100% test. But if you don't need that, then ask your supplier what they recommend. In our microstrip devices that we supply for active antenna applications for TRMs, we are currently doing probably the average is about 1% testing on the basis as, if the process is under control, if the first one's right, they're all right. If the first one's wrong, they're all wrong. So ask your supplier what they would suggest to make it less costly. Hope that's answered the question.
All right, thank you so much, Alan. So we do have some questions from our attendees coming in. As I mentioned, if we don't have time for your question today, do not worry. We will reach out to you following the webinar. So we have a couple that have come in here that are similar, so I'm going to kind of lump these two together for you, Alan. This person is asking, do you take care of anything other than the connection integrated with the housing for meeting EMI, EMC specifications? And then another person is asking about managing demanding EMC leakage requirements, so kind of a requirement or specification questions.
Yep. Can I go back in this presentation to highlight an image to answer that question? Because it's an interesting one. Okay, so I'm going to focus on this part here. So first of all, the connectors are integrated into the housing. Now that's got clear and obvious advantages. So the EMC leakage of the device is essentially the leakage that comes from mating the TNC male to the TNC female. The other thing to bear in mind is the monocoque body that we've got. This is actually a single piece of stainless steel. And we've got internal systems which are designed to, internal gaskets, if you like, which are designed to minimize the leakage. And we do that not only in the junction itself, but we do a similar thing underneath the load. Now, these small dots that you can see on the two gold circles are actually venting holes. Now, they're designed to be below cutoff, so they don't actually leak EMC. And the purpose of these features is to allow the device to vent the internal atmosphere when it's actually being operated in space. So we cope with EMC in two fundamental ways. I think the most important is by design. None of our products are slapped with EcoBond 56C or any other conductive epoxy, so it's all done by design. And of course, having the ability to test it. Now, we can use two ways to test it. We can use a kind of sniff-snort test, which is cheap and cheerful but not desperately accurate, and we can use a reverberation chamber. But for any customers really interested in knowing greater detail about this, we're happy to engage with them and explain in greater detail how we do it internally.
All right, Harold, thank you, or Alan, thank you so much for that answer. So we have another question here from an attendee. How long does it take to get a custom product?
Yeah, it depends on our starting point, Katie. I think I mentioned earlier on, if we've got something, I mean, we've been in this business 25 years. I think we've got something like 300 or 400 SSPA isolator designs. So we can usually start off somewhere close to what our customer's looking for. When we start to push the boundaries, it gets more difficult. But for a standard device, I think we could probably come up with a drawing for our customers within about 4 to 6 weeks, and a prototype within about 14 to 16 weeks. When it comes to really pushing the boat out, and if there are any fundamental things that we've got to work on, then it could be up to six months.
All right, Alan, thank you so much. So we are getting close to the top of the hour. It looks like we're going to take about one more question today, and then we're going to start to wrap things up. So for our attendees, if you have any questions for us, now would be the time to enter them into that Q&A window and click submit. We will reach out to you following the webinar to answer any questions that we get now. And then just a reminder that we have a resource widget with some items in there for you to take with you today. So please feel free to start downloading those things now if you would like to take them with you. All right, Alan, so for today, our last one, what do I need to kick off a discussion to specify this type of component?
The basics. I think obviously making contact with us, giving us as much information as you dare. The very basics would be the operating frequency, the kind of product you're looking for, including the interfaces, the kind of power that you're looking to handle, and the operating environment, whether it's operating in a vacuum or not, and what the fault condition is. You know, in some cases, if it's a full reflection, and this is genuinely the case, then we have to design the isolator for that. If the fault condition is only going to last a fraction of a second, then we can actually develop a device which handles this transient case and is smaller and cheaper, and in many cases actually better. So just be prepared to, you know, share as much information you can, and we will respond in kind.
All right, Alan, thank you so much for answering that last question. As I mentioned, if any attendees have questions that are coming in, we will reach out to you following today's webinar with all of that information. I want to say a huge thank you to Harold and Alan today for giving such a great presentation and for sticking around to answer some of our attendees' questions. We really appreciated the information and having both of you here, so thank you both.
Well, thank you everyone for listening in.
All right, and we are going to wrap things up right there. Thank you to all of our audience members for being part of this webinar event. Take care, and we will speak with you soon.